Hello and welcome to a live stream from Portland State University's Learning Center. This is Chemistry 221, the summer session. And just to get started, I want to paste a few links in our chat for those of you who might be viewing. There is a link to the Learning Center's website as well as a link to their Facebook and Instagram. Definitely check out our website and follow us on Facebook and Instagram so you can get updates on new services we have, new resources we have available to students. That said, today we're going to be working on doing some more dimensional analysis, mainly transforming like grams of a substance or a compound into moles of that compound, or a number of atoms or particles of that compound. So we'll have a lot of fun doing that. We're also going to look at empirical formulas, molecular formulas, and balancing chemical equations as well. So we got a lot to cover, so let's jump right into it. Second here. My screen is weirdly small. So the first problem I want to look at today has to do with calculating the molecular or formula mass of each of the following items. So I've blocked out and kind of redacted a few of them. We're going to deal with just a couple examples of each one. So I tried to pick some of the more complicated ones so we can go over those. This first one, I want to talk about what formula mass is. So the formula mass is the average atomic mass of all the atoms in the molecule. And when I say that, basically what we're going to do is we're going to find out the average mass of each of the atoms, multiply them by the number of atoms we have in that molecule, and then add all of those together. So the first one I want to do is part C. Part C is CaNO3 2. So when we do this, we want to find the atomic mass for each of those atoms. So I'm going to list them down. I want to find the AMU, the atomic mass unit, which is the average mass of calcium. I need to do the same for nitrogen and the same for oxygen. Those are the three different atoms we have in there: calcium, nitrogen, and oxygen. See if we can make this a little bit bigger for y'all. Sorry, I don't know why it's scaled like that. Okay. So to do that, we have to look at our periodic table. So I can zoom over to my periodic table, and to find calcium, which we have up here, that's on group 2, period 4, which is right here. Calcium has an atomic mass of 40.078. So I'm going to slide back over here, go to calcium, which is equal to 40.078. The units for that we think is grams per mole. A mole is really just a number of objects that we have on there. So 1 mole of an object is actually 6.022 times 10 to the 23rd particles, atoms, molecules, anything like that. So it could be anything. You have a mole of pennies, you have that many pennies. So here, if you have that many atoms of calcium, you could weigh out, and it'd be 40.078 grams is what we're saying. We can do the same with nitrogen. Nitrogen's up here on the periodic table. It's in group 15. It's on the second row there, and it has a molecular mass or atomic mass of 14.007. I like to round to 3 decimal places. Just makes the calculations a little bit easier. And most periodic tables do round to those 3. You can get more accurate than that even if you want. Lastly, oxygen, which is a very common one we'll be using. Okay, that's 15.999. It's almost 16, but 15.999. Grams per mole. Now to find the molecular formula mass, we have to add up all of these molar masses or atomic masses and multiply them by the number of atoms in our molecule. So for calcium, we can see we have 1 of them. For nitrogen, we actually have 2 of them because we have 2 of those nitrate groups. For oxygen, we have that 3, but we have to multiply it by that 2 to get 6. So we can add all those up now by saying, I'm just going to write it all down, 40.078 grams per mole plus we have 2 times 14.007 grams per mole plus, and that was 6 times 15.999 grams per mole. And then we can just plug all those into our calculator, and we're going to have our formula mass. So let's do that. Here's my calculator here. I have 40.078 plus 2 times 14.007 plus 6 times 15.999 equals, I have scientific notation there, so that's really 164.086. 164.086. That's in grams per mole. So that's going to be the molecular mass of that object. Let's do part D. Part D is CH3CO2H, acetic acid. And this is, you notice that all the atoms aren't listed together. They kind of broke it up a little bit. It's so we can actually see the structure of that atom. So if there's a hydrogen there, we have a double bond to oxygen, and each of these pivot points are a carbon. This carbon on the end actually has 3 hydrogens attached to it, little methyl group. We'll learn more about that a little bit later, but that's just the way that organic chemists write things, so we can actually see the chemical structure of these atoms. But that said, we have to actually account for each of those atoms in our formula mass when we do it. So we have to sum up the different hydrogens that are there, the different carbons that are there, all as one. So again, finding out the AMU of each of those, we need to find the AMU of carbon, the AMU of hydrogen, and the AMU of oxygen. We already found oxygen. It was 15.999 grams per mole. So let's find hydrogen and carbon. Flipping back over to our periodic table, carbon is up here, group 14, row 2. That's 12.011. So write that down. 12.011. Hydrogen is way up here at the top. That's 1.008. 1.008, and I forgot my units. Let's put those in. Grams per mole. And hydrogen, carbon, and oxygen are things you're going to be using very, very often. You're just going to start to know what those are off the top of your head the more you use them. So have your periodic table handy and know how to look them up when you don't know them. And if you remember them, that's great. Saves you a little bit of time. So to add all these up, we need to add up the total number of each of those atoms we have in there. So for carbon, I have 1 there and 1 there. So I have 2 carbon atoms. So I can write say there's 2 carbons, hydrogens, there's 3 plus the 1. So there's 4 hydrogens. And the oxygens, just 2. So I can use those coefficients now when I'm multiplying everything up. So I can say 2 times 12.011 grams per mole plus we have 4 times 1.008 grams per mole plus 2 times 15.999 grams per mole. And now to add all that up, we just need our calculator. Swipe that over. Let's plug that in. And I get 60.052. There we go, and that's the formula mass of acetic acid. Yeah. So that's kind of the basic idea. All we're really doing is adding up the average atomic mass for each atom in there, and we get this average formula mass for that, or molecular mass. Let's move on to number 10. We're going to use similar ideas, but here we want to find out which of these atoms, either ethanol, formic acid, or water, has the most moles of oxygen. Remember, a mole of oxygen is kind of a number of oxygen, the amount of oxygen atoms in there. So we can do that by looking at that chemical structure and figuring out what is the mole-to-mole ratio between the molecule and the atoms themselves. And that's really a key point in chemistry, because a lot of it comes down to transferring things into moles and finding out that mole-to-mole ratio. So let's look at ethanol first. I'm going to switch to blue. 1 mole of ethanol, which has a chemical formula of C2H5OH. We can see that for each mole, if we look at, we're going to look at each of those atoms, carbon, hydrogen, and oxygen. And for the mole of each mole of carbon divided by the mole of ethanol. So for each mole of ethanol, how many moles of carbon do we have is what I'm asking. And the answer is really just comes down to this number that's right there, 2. So we really have a 2-to-1 ratio for carbon to ethanol. A similar idea, look at moles of hydrogens per mole of ethanol. We can count those up. So here we look at we have a 5 down there, but we have 1 more over here, so we have to add that together. It gives us 6 total. So that'll be a 6-to-1 ratio. The last one is oxygen. The mole of oxygen per mole of ethanol is equal to, we have just 1 oxygen there, so that's a 1-to-1. So if we were to take that atom of ethanol and we break it up into all of its individual atoms, you can see we'll end up with 6 moles of hydrogen, 2 moles of carbon, and 1 mole of oxygen. And that was for ethanol. So let's do the same thing for 1 mole of formic acid. So formic acid is HCO2H. And we can say, look at the hydrogens first. For each mole of hydrogen per mole of formic acid, we have a ratio of 2-to-1. The same is going to be true when we look at carbon. For the mole of carbon per, not the same is true, but mole of formic acid. This ratio is 1-to-1, because there's 1 carbon here for each of the molecules. The last one is oxygen. And really, this question's only asking us about oxygen. It's just a really good practice to work out all of them and just to understand the concept of what we're doing. Oxygens are 2-to-1. There's 2 oxygen atoms per molecule. The last one is water. Water, everyone's fairly familiar with. We have 1 mole of water, which has a chemical formula, H2O. So for every mole of hydrogen per mole of water, that's going to equal 2 to 1. Same idea for every mole of oxygen per mole of water is equal to 1 to 1. So then when they were asking us now, what is the greatest number of moles, greatest number of moles of oxygen atoms in 1 mole of each of these compounds, we just have to look at that molar ratio and compare these ratios together. Which one is the largest ratio? That one's going to be formic acid. Formic acid has more oxygen atoms per atom, per molecule, than any of the other two. And that molar ratio you're going to see come up a lot in chemistry, in this class and the next 2 classes, and further on as well. So number 18 here, we have to determine the number of moles of compound and determine the number of moles of each type of atom in each of the following. So I just picked C and E, which are 2 of the more complicated ones. So for part C, they give us 23 kilograms of calcium carbonate, CaCO3. And we need to determine the number of moles of the compound. So one of the ways we can turn a mass, which is that 23 kilograms, into a moles, the number of moles, is to use its molecular weight, the molecular mass. So first we have to find the molecular mass. And this is what we did in part 3, looking at calcium carbonate in this case. So we have to find the AMU of calcium, the AMU of carbon, the AMU of oxygen. So we can zip back to our periodic table and see that calcium was 40.078. We found that in the first problem we did. 40.078. Carbon, and these are in grams per mole, is the unit. Carbon is 12.011 grams per mole. It's one of the ones I just have memorized. Oxygen, again, we use very often, 15.999. We looked those all up a little bit ago anyways. So now we can find out our atomic weight of this whole thing, the molecular weight. To do that, we have to add these together, plus all the multiples. So we notice that calcium is a 1-to-1 ratio, carbon is a 1-to-1 ratio, but oxygen is a 3-to-1 ratio. So we need to multiply oxygen by 3 when we add them together. So we have 40.078 grams per mole plus 12.011 grams per mole plus 3 times 15.999. Slide that over here and let's plug it in. 40.078 plus 12.011 plus 3 times 15.999. Let's see what that equals. That's 1.00086. Oh, to the 2. So that's 100. Forgot I had scientific notation. 0.086 grams per mole. Now that we have the molecular weight, we can figure out how many moles we have. Because if you look at the units for everything, we have kilograms, which is a mass. If we were to divide that by grams per mole, well, first we have to convert this to grams, and we could get out of that our moles. That should be moles. So that's the basic idea to turn weight of something or mass of something into your moles, is to take your grams and divide by grams per mole, which will give you the moles. You notice dimensionally, looking at the dimensional analysis, the grams and grams are cancel out. And you have per mole on the denominator, so that flips it up to the top and becomes moles. So first we have to convert this grams to moles. So let's look at that, or kilograms to grams. So if I take my 23 kilograms, I need to convert that to grams. So I want some type of grams on the top. I need to put kilograms on the bottom, and I need that ratio for conversion. And so we think, how many grams are in a kilogram? There's 1,000 grams in a kilogram. So if you use that, this number here, this ratio, is really equal to 1 because we have equivalent units there. Another way to write this would be 10 to the negative 3 there, or 10 to the 3 there. Either one of those would work. That's basically the same as saying 1,000. I like to say 1,000 grams. Notice kilograms will cancel out. We're going to be left with grams. Now we have an answer in grams. We could then multiply that by the reciprocal of our atomic mass, which really is just mole per 100.086 grams. Now the grams are going to cancel out there and there, leaving us with a unit of moles, and we can just do the math going across. So that's 23 times 1,000 divided by 100.086. And I got two, let's say, I need that back. 29, let's say that's going to be 230 because we're rounding to two significant figures. Oh, I should be in moles. 230 moles. So since we had two significant figures here, we need to make sure our answer is in two significant figures. So we could have written 229. Even if we rounded to three significant figures, it'd still be 230. But the difference is we don't put this little dot here because we're only doing two sig figs. So that's how many moles are going to be in that calcium carbonate. But we also need to find the number of moles of each type of atom. So that comes down to that mole to mole ratio. Now we know, like we said, the mole to mole ratio of calcium is 1 to 1. For every molecule we have one atom of calcium. So I can multiply 230 moles times, now we can put this as moles of calcium carbonate, multiply that times this ratio of 1 mole of calcium per mole of calcium carbonate. When I do that, see the moles of calcium carbonate cancel out, and we left with 230 moles of calcium. It seems a little weird to do that because it's really just a 1-to-1, but that basic step is what we need to do for everything when we're talking about that mole to mole ratio. We're trying to see how does this mole of this compound compare to the mole of this atom. And we're going to do that the same with carbon. It'll be exactly the same because the ratio is the same. 1 mole of carbon divided by 1 mole calcium carbonate, which is going to be equal to 230 moles of carbon. The last one is oxygen. The oxygen, we said, had 3 in there. So our mole to mole ratio for that is going to be different. So we're going to multiply this by 3 moles of oxygen for every 1 mole of calcium carbonate. Just cancel my units above, cancel my units below. That's going to give us, we can multiply by 3 and round to 2 significant figures. That's 690 mole of oxygen. So that tells us the number of moles of each of those. I'm going to shrink some of that down so I have some space for the next one. Yoink. Okay. Should be good. For the next problem is E, which is telling me I have 0.125 milligrams of caffeine. Caffeine being C8H10N4O2. So this is a lot more atoms, and there are a lot more of each of them. So we have to kind of multiply the ratio of moles to moles is going to be different for each of these guys. We can apply that same formula. Just by multiplying that ratio by the total number of moles of the atom, we'll be able to find out the moles of each of those atoms in that. So first, let's start with the weight. Here we have 0.125 milligrams of caffeine. Before we had 23 kilograms. So we had a lot of that calcium carbonate. We have a tiny bit of caffeine. So let's first figure out our molecular weight. So to do that, we need to find the AMU of carbon, AMU of hydrogen, AMU of nitrogen, and the AMU of oxygen. Carbon is 12.011 grams per mole. Just looking up on our periodic table, these are the common ones that we use a lot. Grams per mole of hydrogen. Nitrogen, we haven't looked up yet today, but I believe it's 14.007. Yep. That's 14.007 grams per mole. Oxygen, we deal with all the time. And now we need to figure out the molecular mass of this. So it's just the same as we did before. We just have a lot more coefficients to work with. Now it's 8 times 12.011 plus 10 times 1.008 plus 4 times 14.007 plus 2 times 15.999. The units for that is grams per mole. I'm going to put brackets around there so it's proper, and we can pull out our calculator and see what we get. So it's 8 times 12.011 plus 10 times 1.08 plus 4 times 14.007 plus 2 times 15.999. And that's going to be 194.194. That is grams per mole. So now that we have the atomic mass, we can figure out how many moles of caffeine we have total. So to do that, we have to take our 0.125 milligrams and convert it into grams. So we could multiply by some ratio, that dimensional analysis ratio, putting milligrams on the bottom, grams on the top, and we need to make sure that's equal to 1. We can do that. This time I'm going to say put 10 to the minus 3 up on top, because 10 to the minus 3 grams is equal to a milligram. So now our unit-wise will equal grams. So now we can multiply by some number of grams for grams per mole. That cancels out our grams and leaves us behind with moles. So this will tell us the number of moles of caffeine molecules we have. Let's plug that into our calculator. 0.125 times 10 to the power of negative 3 times, I guess divided by 194.194 is equal to, I got 6.4, and we got 3 significant figures, 4 moles. Oh, it should be times 10 to the negative 7. Times 10 to the negative 7. So I have that negative 7 over there. Hey, you can't see my calculator, can you? Something's wrong with my thing. Wonder why that's doing that. Let me exit out of that. Let's see all of that. Open this. Swipe that over. No. Aha. I think I figured that out. Okay. Sorry about that. Little technical difficulty there. Now you can see my calculator. I apologize. So, plugging it all in, we can see that's 6.44 times 10 to the negative 7, and the units for that is in moles. That's how many moles of caffeine molecules we have. We now need to convert them to the moles of each of the individual compounds. I'm going to do that on the next page. I'm going to copy, this is the moles of caffeine that I have. Go ahead and copy that over. There we go. So that's moles of C8H10N4O2. And we need to now multiply that by the mole-to-mole ratio of each of the different atoms. Let's start with carbon. You can see carbon has C8, which means there's 8 moles of carbon for every mole of caffeine. So we can figure out what that is just by multiplying this number we have here times 8. The 8-to-1 ratio gives us 5.15. 5.15 times 10 to the negative 6. And that's moles of caffeine. Or moles of carbon. Because caffeine got canceled out. Do the same thing, just pasting that same number. Give me my moles of caffeine. C8H10N4O2. I'm going to multiply that. I'm going to do hydrogen next. So that's a 10-to-1 ratio. So caffeine and caffeine cancel out. That's left with, that's just times 10. So that's a pretty easy calculation. We're really just going to be 10 to the negative 6 now. There you go. Everything else stays the same. 6.44 times 10 to the negative 6 moles of hydrogen. Next one is nitrogen. Pasting in. Ooh, that came in as a number. That's weird. Undo. I'll just rewrite it. It's 6.44 times 10 to the negative 7 moles of C8H10N4O2. Slide that down just a little bit. I'm going to multiply that by the molar ratio of nitrogen. So for each atom there's, for each molecule there's 4 moles of nitrogen per mole of caffeine. Which, plugging that in, multiply by 4, we get 2.57 times 10 to the negative 6. Nitrogen. And then lastly, oxygen. 6.44 times 10 to negative 7 mole C8H10 N4O2 times 2 moles of oxygen per mole of caffeine is equal to same number we were dealing with, but just times 2. 1.29 times 10 to the negative 6. 1.29 times 10 to the negative 6 moles of oxygen. And that will tell us then, now we know how many moles of each of the atoms are actually in there. Do my cancellation for dimensional analysis. And we're good. So you see, for this problem, we had a mass and we were turning into a mole. And to do that, we used the molecular weight of everything, the molecular mass, by taking the mass we had, dividing by the grams per mole to get us into a value of moles. We could then use that mole to mole ratio to determine how many moles of each of those atoms we had. This next problem, we're going to kind of do the opposite. We're going to determine the mass based on the number of moles we have. So in this one, instead of dividing, we're going to multiply. Take the moles of the molecule, and we're going to multiply that by the atomic mass of the molecule. If we look at that by units, that's moles times grams per mole, which is equal to grams. Notice moles are going to cancel out. So if you're ever confused about where to go, think about what you have, where you need to go with it, and try to make the units work by doing some dimensional analysis. And you're most likely going to be on the right track. Just make sure you're multiplying the right units with the right units. If you have kilograms to grams, make sure you convert, milligrams to kilograms, make sure you convert, stuff like that. So let's tackle these two, D and E. So for part D, that's 1.23 times 10 to the third mole of fructose, C6H12O6. And we want to find the mass of each of these. So again, we have to find the atomic mass of the molecule itself. I guess that's not AMU anymore, it's molar mass. That's what I should be writing there. So the molar mass is going to be that same thing. We need to find the AMU of carbon, AMU of hydrogen, and the AMU of oxygen. Luckily, these are all things we've worked with in the past, so we can know that's 12.01 grams per mole. Hydrogen is 1.008 grams per mole. Oxygen is 15.999 grams per mole. And we can always look that up on our periodic table. So the molar mass of the molecule would then be, using the ratios in the formula that we have, we can say 6 times 12.011 plus, that should be a plus, that's a terrible looking plus, that's better, plus 12 times 1.008 plus 6 times 15.999, put some brackets through our units, gram per mole, and then we can add all of those up. I'm going to clear my calculator, go 6 times 12.011, missed my multiplication, insert it back in there. Alright, plus 12 times 1.008 plus 6 times 15.999. And we'll say that's 180.156 grams per mole. So that's our molecular mass. That's how many grams per mole we're going to have. If we weighed out 180.156 grams of this substance, we would have exactly, or pretty close to, 1 mole of it. So Now that we have that, we can determine what is the mass based on these number of moles. So we can take our moles, just like we said up here, we're just multiplying the moles times the molecular mass. 1.23 times 10 to the third mole. I'm going to multiply that by 180.156 grams per mole. When we do that, our moles cancel out and we get grams. So 1.23, I'm going to use the e to the 3, that's the times 10 to the third power. I'm going to multiply that by this value we got up here, and we get 2.22, doing the 3 significant figures, times 10 to the 5 grams. Since it's 10 to the 5, we can convert to kilograms. To do that, we want to multiply this by kilograms over grams. This is 1,000 grams. Or we can use 10 to the 3 on the bottom, just so we can see that 10 to the 5 and 10 to the 3 is going to leave us with 10 to the 2, which is equal then to 2.22 times 10 to the 2 kilograms. Now got to put that unit on. Oh, you can't see my thing there. Kilograms. So that's the mass that we have based on that number of moles. Doing the same for E, part E, now we have 0.5758 mole of iron sulfate with hydrogen, or with water, FeFSO4, and we have 7 moles of water in there. So we can do the same thing here, finding the molecular weights for all of these, or the atomic AMU of Fe, AMU of S, sulfur, AMU of oxygen, AMU hydrogen, and we have oxygen on there already. So iron, we haven't looked up iron yet today. Got 55.845 for iron. That's a group 8 transition metal. It's in that main D block in the middle of your periodic table. So what did I say it was? I talked too much. 55.845. 55.845 grams per mole. Sulfur, 32.065. Let's hop. .065 grams per mole. Oxygen, again, one that we know fairly well. Dealt with it several times today. 15.999. And hydrogen, again, we've dealt with that several times today. 1.008 grams per mole. So now we just need to multiply these by the number of atoms per molecule that we have for each of those. Well, for iron, that's going to be 1. For sulfur, that's 1. For oxygen, that's 4, plus the 7 from the water, right? So it's really, oxygen is 11. Hydrogen is, there's 2 in the water, but there's 7 waters. So that means that we have 14, really. Each 14. So we can multiply these all out now by saying 55, or add them all up. 845 plus 32.065 plus 11 times 15.999 plus 14 times 1.008, and that's it. We already added the oxygen from the water into the other ones, so we're good. Put our units on there, gram per mole. Adding all those up, 55.845 plus the 32.065 plus 11. Of course, ones would be a good thing to type there. 11.5 times 15.999 plus 14 times 1.008 all equals 278. And yeah, we'll leave it at 278.011. Yeah. So now all we have to do is multiply. Take that number of moles we have. Again, this is in grams per mole. And we multiply 0.5758 moles times 278.011 grams per mole. When we do that, 0.5758 times 278.011 equal to 160.01. And that's going to be in the units, grams. So that is, again, how we find the mass of our compound, dependent on how many moles we have. And this is useful because in a chemical reaction, you can often tell, well, how many moles reacted, and then you can use that to figure out how much mass you have, or vice versa. If you can determine the weight of your product, you can then figure out how many moles of it reacted. I should also point that there's sometimes an easier way to find the molecular mass. In the modern world that we live in today, you can just look up these things. So a lot of these things are tabulated on the internet. Do a quick Google search for what's the molar mass of this compound, and you're actually going to get 278.02 is what it'll tell you. And they just use slightly different values for the molecular mass than I did, but it all comes out to the same mass at the end of the day, just because it gets lost in sig figs, the difference. But once you understand how they got that, is really just by adding up the different ratios, different combinations of the molecular masses for each atom in the molecule. So the next thing we're going to do is one of the most key things we can do is determining the empirical and molecular formulas. So we're going to start out with the percent composition. Okay. This is in 3.2 now. So to determine the percent composition of, I'm going to skip to just this one because I'm starting to run out of time. I'm going to skip part A and go straight to part B. The percent composition of TNT, which is C6H2CH3 NO2 3. So to do this, the formula I like to use is you find the percent of the atom, right? And to do that, we kind of that's going to be equal to the AMU of the atom per, say, molar mass of the molecule. We're going to multiply that ratio by 100%. So since it's giving us a percentage, we basically assume we have kind of 1 mole of this stuff, and we just kind of work our way from there. So to do that, first we have to find the AMU of every atom in this. So again, AMU of carbon, AMU of hydrogen, AMU of nitrogen, and AMU of oxygen. These are all values. Again, look them up on your periodic table. I'm going to fill them in. When you work with it enough, you just start to know what they are. 15.999 grams per mole. And then we have to find the molecular weight of it. Molecular mass. The molar mass. Which is going to be equal to carbons. I have 6 plus 1. So that's 7. So 7 times 12.011 grams per mole. Plus, we're going to add to that hydrogens. We have 2 plus 3. So that's 5 total. 5 times 1.008 plus nitrogen. We have 3 nitrogens. We have this nitrate group times 3. So that's 14, or 3 times 14, 14.007. And we're going to add to that the oxygens. There are 6 oxygens times 15.999. These are all in grams per mole. Math, putting it all into our calculator. 5 times 1.008 plus 3 times 14.007 plus 6 times 15.999. This is equal to 227.132 grams per mole. So now that we have the molecular mass of the molecule, that's what we were just finding there. We have the AMU of each atom, which is listed over here on the left. We can then determine the percentage of each atom. So starting out, percentage of carbon, the percent of carbon is going to be equal to 12.011 grams per mole divided by 227.132 grams per mole times 100%. The one thing that we do have to do in here that we haven't accounted for, and I should probably rewrite this up here, is we need to account for that mole to mole ratio. So I need to do the mole of atoms versus the mole of the molecule. That mole to mole ratio again comes into play. So in this case, it's going to be, we said a 7 to 1 for carbon. So that's 7 mole carbon per 1 mole of, this is TNT. That's a short word for it. So now we can get our percent composition, 12.011 divided by molecular mass times 7 times 100. It's going to be 37.02. That's a percent. Next one is the percentage of hydrogen, which is 1.0808 grams per mole. Divide by 227.132 gram per mole. Multiply that by its ratio, we said was 5 to 1. So that's 5 moles of hydrogen per 1 mole TNT. Times 100% is equal to, clear that, 1.008. So you divide by, I guess I do need this number, times 5 times 500 is equal to 2.22. 2.22%. Guess I can take that one more decimal place out, keeping everything to 4 suffix, 2.219. Next is nitrogen. The percent nitrogen is equal to 14.007 gram per mole divided by 227.132 grams per mole. And multiply that by 3 to 1 mole of nitrogen per mole of TNT times 100% is going to be equal divided by this guy times 3 times 300 or 100. 18.501. That's 4.6. That's good. That's our percent there. Last one is oxygen. To 7.132. These are grams per mole. I'm going to multiply that by our ratio. We had 6 oxygens per molecule, so that's 6 moles of oxygen per mole of TNT. Multiply by 100%. That's just to give us a percentage instead of a decimal. 15.999 divided by that guy times 6 equal to, and here I'm getting, I had to multiply by 100 still. Forgot to do that. 42.24. 42.24%. And there we have our percent compositions for each of them. Carbon, hydrogen, nitrogen, oxygen are these percentages on the left. One way to check yourself to make sure you did all the math right is add each of those together. And if you did it right, let's hope I did, you get pretty close to 100%. There's a little bit of rounding in there. We should get right around 100%. So that's good. See, we are about out of time. Determine the empirical formulas for that. That's good. Let's do that one. We'll keep blazing through it. For part A, I don't know if I have enough time to do that one. Those are the 3 I really wanted to do. Okay, so for part A, we want to determine the empirical formulas for the compound with the following percentages. So those percentages are percentages by mass. So the steps for doing this, we want to assume we have 100 grams of a compound. Whatever compound we're talking about. Which gives us then that the percentage of the atoms that they give us, the mass percentage, is going to be equal to the grams of atoms. It just makes that conversion a lot easier. Second part of that is we take the mass of those atoms that we find. We want to divide that by the AMU of those atoms. So the atomic mass of those is what we want to divide by. That basically just gives us the moles of atoms. Once we do that, we can then divide. So we want to divide. I have to do that for each of those percentages. Then we divide each mole, each of the moles of atoms, by the lesser moles of atoms. So whatever atom by the lesser. Can't talk and write at the same time. So whichever atom has the least amount of moles, we take that value and divide all the moles by that. So the least one should always equal 1, and everything else should be some multiple of that. Something higher number. The last step, 4, is to scale the ratios. And we do that by, so a lot of times when you do this, you don't get a whole number for each of those. So we have to scale everything by the same number, so everything's a whole number ratio, which is ultimately what we want to do. So for part A, we know we have 43.6% phosphorus. We want to, which means that that gives us, assuming we have 100 grams of this, that's 43.6 grams of phosphorus. We can then multiply that by the molar ratio. If you look up phosphorus, you see that it's 30.977 grams per mole. So I put the 30.977 grams on the bottom, the moles on the top. It's still a ratio of 1. We're converting the grams to moles here. So the grams and grams go away. That is going to equal 43.6 divided by 30.977. That's 1.41. 1.41 moles of phosphorus. The next one is 56.4%, and that's going to be oxygen. So that tells us we have 56.4 grams. We can multiply that by the moles of oxygen, which is 15.999 grams per mole. It's going to cancel our grams, convert it into moles, which is what we want. We get 56.4 divided by 15.999, which is 3.52. Yeah. Say 3.53 moles of oxygen. Now we notice we have these two here. Neither one of them are whole numbers. The lesser mole is going to be this top one there. So I'm going to divide each of them by 1.41. Okay, which is going to equal 1 for that case. 3.53 divided by 1.41 is going to equal 3.53 divided by that one. That's 2.5. So we could write this as a molecular formula or an empirical formula of PO 2.5. But we don't have whole numbers there. So what we need to do is we need to multiply both of those values by something that'll give us a whole number for both of them. And we want the smallest whole number possible. So I'm going to multiply each of them by 2. If I multiply those by 2, I'll just say times 2. We're going to get P2O5. That is our empirical formula for this one. Let's skip part B. B is the same idea. It's just we have K, H, P, and O. So we have 4 different things, and we end up having to kind of work it a little bit more. But it's the same basic idea. You want to follow these same rules. Assume we have 100 grams. That turns your percentage into a gram. We then take the mass of all of the atoms that we have in grams, divide it by your AMU to turn it into moles. Do that for every step, and then we can divide by the lesser mole to find the ratio between the different atoms. Make sure to scale it so you have the least number of whole atoms at the end, and you've got an empirical formula. This next one here, we're going to find the molecular formula, which the first step is to find the empirical formula. So for these steps, for part 1, I say find empirical formula. This is part 1. Part 2, we want to divide the molar mass of the empirical formula we want to divide that by the molar mass given. In this case, they give us the molar mass of dichloromethane, 99 grams per mole. And that determines determines a multiplier. So that multiplier we take, once we find our empirical formula, we multiply all of the atoms in there by this multiplier to find the molecular formula. So let's do that real quick here. So finding the AMU, this is dichloromethane. They say it contains carbon, hydrogen, and chlorine. So we need to find carbon, AMU of hydrogen, and AMU of chlorine. So I know carbon, 12.011 grams per mole. I know hydrogen, 1.008 grams per mole. I know chlorine. I don't know chlorine actually, but we can find it out. Hop over to our periodic table. Chlorine's right over here next to sulfur, 35.453. Hop back down to here, 35.453. 35.453 grams per mole. So now we need to determine our molecular mass. So it does tell us the percentages. That's what we need to work off of. So we know that the percentage of carbon is 24.3% carbon, which tells us that with 100 grams of it, we have 24.3 grams of carbon. So if we divide by 12.011 grams per mole of that, grams are going to cancel out. We're going to get the moles of carbon. So let's do 24.3 times 12.011. We're going to say that's 291.9. Let's say 292. Where am I? Here. 291. I feel like I'm doing that wrong. I multiplied. That's what the problem is. Haha. That seemed like a really big number to me, so I second guessed myself. I'm going to divide by 12.011. That looks way better. Okay. 2.02 moles. We do the same for the percent of hydrogen they give us, 4.1% of hydrogen, which turns into 4.1 grams of hydrogen divided by 1.008 grams per mole. That will give us the moles of hydrogen, which is 4.07 moles. Really, we want to round that up to 2 sig figs, 4.1 moles. So the last one is chlorine. They don't tell us the percentage of chlorine, but we can derive that if it's the only other thing left. So let's say percentage Cl, which should be equal to 100%, minus 24.3 minus 4.1, which will equal 71.6%. So that infers a weight, a mass, 71.6 grams. Divide that then by our atomic mass, 35.453 grams per mole. This tells us the number of moles. Divide that, 35.453. That's 2.02 moles. So now for each of these we have to find and divide by the lesser mole. The least mole is basically the same for carbon and chlorine, which means they probably have the same number of atoms in the molecule. So in this case, we can divide for carbon is, say, 2.02 mole divided by 2.02 mole. Obviously going to equal 1. So there's 1 carbon on the empirical formula. Looking at the hydrogen, that's going to be 4.01 divided by 2.02. The moles are going to really just cancel out here for this ratio. 4.01, this should be about 2. Oh, that should be deleted. 0.1 divided by, there we go. I wrote it wrong, 2.03. So 2.03 is what I'm getting there. If we round to 2 sig figs, we get 2.0, which is good. And the last one is chlorine. That was for hydrogen. Chlorine is 2.02 mole divided by 2.02 mole. 1 chlorine. So our empirical formula, CH2Cl, is there. So now we can find, this corresponds to a molecular mass, and we can find that by adding up the molecular weights of each of those with their multiples. So that would be 12.011 plus 2 times 1.008 plus, was it 35.453, and that would be grams per mole. 12.011 plus 2 times 1.008 plus 35.453 is 49.48. 49.48 grams per mole. So that's the molecular mass of the empirical formula. We know that the sample we had 99 grams per mole. So we can then take 99 grams per mole, divide by 49.48 grams per mole, and that'll tell us this multiplier we're looking for. So take 99 divided by that guy, we get 2. Nice big even 2, pretty even. So we can take our empirical formula, CH2Cl, and we want to put little brackets around it and say there's 2 of those. So we can distribute that 2 amongst everything, and that's C2H4Cl2, which is our molecular formula. So you see, the molecular formula is pretty easy to get once you find the empirical formula. Just find your molecular mass of that empirical formula, and you need to have a known molecular formula for what you're looking for, and then you can figure out, or a known molecular mass of what you're looking for. The last thing I want to cover, I know I've gone over, so thank you for sticking with me, but this is an important thing we need to cover today because we won't have time for it next week. We had a lot of stuff to cover next week, is balancing the following chemical equations. And when you balance chemical equations, there's really 2 things you really need to worry about. The key part of it all, the most important thing, I'll put up 3 exclamation points. That's how important it is that each side, if I can spell, that'd be good, of the equation must have the same number of atoms. Number of each atom. Which means if on the left side you have 5 carbons, on the right side you also have to have 5 carbons. If on the left side of the arrow you have 3 hydrogens, on the right side you have to have 3 hydrogens. There needs to be a balance of atoms. So we're not going to lose any atoms. No atoms are changing to other atoms in this case. They are all going to just be shifting around within the molecules. So you need to have that balance. That's why we call it a balanced chemical equation. There needs to be a balance of atoms there. The other part, when we're talking about the chemical equations is we usually use the lowest whole number coefficients. I hope I'm spelling this right. I think I am. Okay. So what that means is no fractions in the coefficients. Sometimes you might see fractions in the coefficients. They're not exactly balanced chemical equations. We use those sometimes for the equation of formation of different things. But whenever we're talking about a balanced chemical equation, we always have whole numbers and the lowest whole number. So there should be no common factors of any of the coefficients and the lowest possible numbers you can have. So let's look over a few of these. I'm going to jump into the first one. For part A, this is Ag solid plus H2S gas plus O2 gas. It's going to produce Ag2S plus H2O liquid. So looking at this, first thing I'm going to look at is making sure that the more complicated ones are balanced on either side. So here I have one sulfur and I have one sulfur. That's a good sign right there. I have two hydrogens. That's a good sign right there. But I have two oxygens here. I have one oxygen there. So I know this has to double. I have to have twice as much water as I originally had on there. And that changes a few things, right? Because now I have four hydrogens here. I need to go back. I need to double this as well. Oops. So I need to have two hydrogens there. So that gives me four hydrogens. Now I have two sulfurs. So I need to have two sulfurs here. And then finally, or maybe not finally, that brings me back to a 4 of the silver. Because I have two silvers times the 2 that's there, giving me 4. The last thing I need to look at is this oxygen. So here I have two oxygens. Now I have two oxygens. I'm set. So I can double check. 4 silver, 4 silver, 4 hydrogens, 4 hydrogens, two sulfurs. We have to multiply that by 2. 2 sulfurs here, 2 oxygens, 2 oxygens, and that one's balanced. Look at the coefficients to make sure they're the lowest whole number we can have. I'm going to throw that 1 in there just so it's easier to read. 4, 2, 1, 2, 2. The 1 is essentially a prime number, not exactly, but we can't divide by any. There's no common factors between those. So I'm going to say we're good. I'm going to look at, I'm going to skip part C and go to part E. And we'll end it after that one. Which one was? Let's go down to part G. Part G was a little trickier. So I'm going to cover that. So we have aluminum, which is a solid, plus H2SO4, which is an acid. So it's aqueous. And producing aluminum to sulfate, which is a solid. Oops. Plus H2 gas. So again, starting with the more complicated ones, first thing I look at is my sulfates here and here. I see SO4 has 3, so I need to balance that SO4 over here. So I'm going to throw a 3 in front there. And it's a lot of manipulating things and kind of working it back and forth until you get the right ratios of everything. So then I'm going to look, because this is happy, I'm going to look at the hydrogens. Well, I just have to throw a 3 out in front of that hydrogen, and that one's pretty happy. The last one is aluminum. Aluminum has just 2 there, so that needs to be a 2 there. Actually, that wasn't so bad, was it? We have 2 aluminums on each side, 6 hydrogens on each side, 6 of the sulfates, or 3 of the sulfates, sorry. 3 there and 3 there, and we're good. Let me jump back up to E, because I think that was the tricky one. So E, SC, leave a little space, SC2, O3, solid plus SO3 liquid produces SC2 SO4 3 solid. So in balancing these, again, the first thing I'm going to look at are the more complicated ones, right? So they're all fairly complex. We have these two bonded together, these two bonded together with a bunch of that there. This SO4 is different than the SO3 here, so we have to make sure we count sulfur and oxygen separately. So let's start with sulfurs. Why not? There's 3 sulfurs here. So I'm going to look over and say, okay, this probably needs a 3 in front of it. Let's start there. I see there is 2 of the scantiums. I believe that's how you pronounce that. The SC2, so we're happy so far. So let's look at oxygen. So we have 3 there, and we have 3 times 3 is 9 there. So that's 11. No, that's 12 total. Here, we have 12 oxygens. We're actually pretty happy. All right, and that's that. Okay, so that's the idea of balancing chemical equations. Make sure that each side has the right number of atoms back and forth, and we have the lowest whole number of coefficients. That's all I have for you today. I know I went 20 minutes over or so. If you have any questions, I do have drop-in hours just after this. Go into Pingy, look for chemistry or chemistry 221 drop-in, and drop in and say hi and ask me any questions. I'm happy to help you out with any questions you have. You can also schedule an appointment with Amir. He's our chemistry tutor during the week. I think he has hours most of the days of the week during different parts. So check out the Pingy schedule there as well. Have a great day and enjoy.